In this video, I'm going to talk about linear programming. Let's try to rethink about a typical mathematical modeling. In a mathematical modeling, we have objective, we have constraints, and we have some decision variables. Of course, you typically need to come up with those kinds of the decision variables at first in order to build a model and think about all the potential constraints. Constraint, when we talk about constraint, actually it's kinds of you have limited resources. For example, you don't have infinite money, right? And you don't have a huge office, probably you are imagining you are going to have. So you do have a limited resources as constraints. And suppose you already have your objective, you have decision variables, you have constraints, and you want to write down as a mathematical model. In a mathematical models, you are going to typically maximize or minimize your objective. For example, you want to maximize your profit or you minimize the cost. And if we are going to write down in mathematical form, we are going to maximize or minimize f in terms of x1, x2, x3, x4, and xn. The f is the function, x1, x2, and xn are those independent variables. So we are going to maximize or minimize the f, subject to constraints, right? So we have different type of constraints. For example, we have f1 in terms of x1, x2, xn less or equal b1, or we have f2 in terms of x1, x2, xn will be larger or equal b2, or we have fk in terms of x1, x2, xn larger or equal bk, or we have fm in terms of x1, x2 less or equal bm, something like that. So you can have all kinds of constraints you have, and I just make up some of them like that for you. If all these constraints and all the objective functions you have are in linear form, when I say in linear form, it means all those equations will be linear to the independent variables. If you have such a very nice models, we call linear programming. For example, instead of maximize or minimize the f in a very complex form, you have maximize or minimize c1 times x1 plus c2 times x2 plus cn times xn. Subject to the constraint will be in linear form as well. For example, you have a11 times x1 plus a12 times x2 plus, keep going, plus a1n times xn will be less or equal b1. You might have ak1 x1 plus ak2 times x2 plus plus akn times xn larger or equal bk. And you can keep it going until you hit all the constraints. So the typical property of linear programming is every equation you have are in linear form. You need to make sure you don't have any nonlinear component over there. For example, you have x1 times x2. That is a nonlinear component. And if you have any nonlinear component, your linear programming actually is no longer linear. It immediately becomes nonlinear programming. And in this case, we don't want to go to nonlinear programming because it's so difficult to solve. The reason we focus on linear programming because it is solvable in a polynomial time. The history of linear programming can be tracked back to 1939 when the Russian scientist Leonid introduced linear programming to the world. Since then, linear programming has been applied in a wide variety of industries. Especially in economics, it has been applied a lot in all types of problems. For example, you try to find the optimal financing issues, and you try to identify what is the optimal interest rate. You try to figure out what is the optimal combination of those different types of stocks. You can all use linear programming. And because of the huge impact of the linear programming, they give the 1975 Nobel Prize to linear programming to Leonid. And of course, there are many other scientists also contribute to the linear programming. And because of that, linear programming has been widely applied in World War II as well. The reason we need linear programming is because we have huge logistical issues in the wars. And those scientists can use linear programming to optimize the logistical issues when the army is marching from one country to the other. About linear programming, I would like to mention a couple of scientists. The first one is called George Dantzig. George Dantzig actually is a professor in Stanford, and he invented the simplest approach. So what is the simplest approach? Actually, there's a matrix transformation approaches that can solve the linear programming problem in a relatively quickly method. So sometimes it's very difficult for you to solve a maximization problem. You can transform it into a minimization problem so that you can solve that much easily.